So, greetings to our esteemed attendees. A warm welcome to Tata Alexis of Highway webinar. I am delighted to introduce you to this fascinating topic of the moment. So, before going into our topic, I'll just give you an overview about Tata Alexi. So, Tata Alexi is a subsidiary of the esteemed Tata Group. With a rich heritage of 150 years, the Tata Group has emerged as a global powerhouse, driving innovation, social progress, and economic growth in over 100 countries, employing a diverse and talented workforce of close to 1 million employees. With a remarkable track record of over 33 years, Tata Elxsi stands as a prominent name among the leading product engineering service providers with a global presence across industries including transportation, broadcast and communication, and also healthcare. And coming to the transportation business unit of Tata Elxsi, we have an impressive legacy of 25 plus years with Tata Elxsi successfully handling three core businesses of the transportation sector, which are automotive, off-highway vehicle, and rail. And we have 65 plus global customers currently with us. We engineer future mobility solutions to help us build the best in class transport and to offer an intuitive passenger experience to our customers and end users. So now I would like you all to meet our expert speakers, Rajesh R, Senior Manager, Transportation, and Dr. Anjana P. Das, Specialist of Transportation Business Unit. So they will be sharing their insights on how this cutting edge digital solution can address major challenges currently being faced by the international off-highway industry. Now, please feel free to type in your queries in the messaging window available to you. So we will try to address them during the question and answer session. And I'm not going to bore you guys with any more details. So now let us dive straight ahead into the session. Over to you, Anjana.
Thank you, Ashwin, for the detailed introduction. Today, in this webinar, we are going to give you an overview about our operator assistance solutions, then the use cases associated with this off-highway market, then the challenges associated with the use cases, challenges in the development of the solutions, approach towards solving those issues, and Tata Lexi's solution accelerators, and finally, a few of our work samples.
Yeah, let us look into the operator assistance solutions. The operator assistance solutions can be put into two buckets, like perception solutions, handling run view, terrain mapping, a transparent vehicle, and implement safety and object handling. And automation of operations can be the other bucket, where we have the trailer hitch support, implement automation, auto parking, end user testing, etc.
And why industry needs such operator assistance solution? One of the requirement is, of course, these operator assistance solutions can reduce the dependency of manpower, and it helps in the ease of operation of these vehicles. And of course, it helps in providing safety and convenience to the operator. And in some cases, these vehicles are supposed to be operated continuously for a long duration of time. In such cases, it helps in these endurance trials. Then it may be supposed to work in all day, night, and all weather conditions. And in some cases, it may require these remote operations, remote assistance operations, and all. In all these, factors demand the need of operator assistance of highway market, of heavy vehicles in the market, and since we Tata Elxsi are focusing on this segment.
Let us look into typical use cases. The use cases are like operator assistance, safety teleoperations, and endurance trials, unmanned operations, and equipment safety. And when you consider this operator assistance solutions, it can be like assistance for the turn or parking, especially when the trailer is hitched to the vehicle, and maybe for the precision motion and the farming application, and could be the trailer hitch assistance, hitching the maybe the guidance for the trailer hitch, or it could be just for the, it may be the autonomous trailer hitching, and terrain view solutions will come under the operator assistance. And coming to the safety side, it can be like a hazardous operation handling and accident prevention, and the transparent bucket, transparent vehicle. Then on the tele operation side, it can be like a purely remote control for handling the remote hazard operations, or tele-assistance as an assistance for the autonomous operation. And considering the endurance trial, when considering the driver availability, uh, automation will help you to run the endurance trial, maybe running for 24 to 48 hours in the unmanned operations. Then for the equipment safety, solutions can be for this implement protection or the vehicle stability.
Yeah, then comes the demand. As we mentioned, we have a lot of features and solutions, and we can see a huge demand from the customer, especially in the autonomous trailer handling, trailer hitch assistance. Then coming to the excavator, this transparent bucket features for excavator, then endurance testing for tractors, toppling prevention of tractor, implement the protection of various protection features for tractors. Then it comes into the agricultural segment, precision seeder. Then in the solar field maintenance vehicle, in all these areas, we could see a huge demand from our customers.
Then there can be different levels of automation, starting from the operator convenience to semi-automated operations, where you have the partial automation implemented, to the fully autonomous operations. We'll be discussing more into this different use cases in the upcoming slides.
Yeah, I mean, these operator assistance solutions, I mean, the challenges basically associated with this solution, we can categorize into two. We can see it in a two different aspects. One aspect is, I mean, the use case itself, some use cases itself is complex, and solving and developing algorithms to solve such use case. That is the one pillar we can see. And another, segment is like the complexity is associated with developing the use cases in the development process. Since hybrid algorithms are using, so that complexity is another factor.
Let us discuss the solution challenges. And when you consider the solutions, there will be diversities in the use cases, especially in the off-road segment. Considering comparing to the automotive segment, the off-road segment will have a lot of diversities in the use cases, and that will add to the complexities. And there may be requirements for the precision maneuvering and extended perception, much beyond the vehicle in the elevation side and azimuth side, and all-weather operations. Such things will, the use case will add the complexities. And the localization and the motion tracking is a huge challenge in the off-road segment, especially in the unstructured environment. The dependency on multiple sensors would be required for localization and motion tracking. And when coming to the sensor technology, and a lot of processing requirement will be there when you are using the lidar sensors to handle the degraded vision situations, and the cost is also involved associated with the different sensors. Then the powering requirement is a challenge, especially to handle the automation requirements, putting the actuators and other power devices. That power management is an issue.
Yeah, another, now we are looking on to the different challenges associated with the use cases. I mean, what are the different challenging use cases? One is the degraded visibility. That means the environment itself is challenging due to dust, fog, rain, low light conditions, completely dark situations. And these aspects of operational requirement call for solutions around sensors like LIDARs, cameras, IMUs, and multiple sensors.
Another one is the weather impact. Due to the weather conditions, whatever sensors we are using, it should be rugged enough to handle that. And it might require specialized enclosures, rugged enclosures, and a special cleaning mechanism to deploy in the field.
Another important challenge is the issues, the complexities associated with mapping and localization of this unstructured environment. Most of the cases, it is very, since the environment is highly dynamic and some cases it is very difficult to represent even the boundary of the drivable region. In some cases, need to consider the uneven terrain and complex vehicle orientations has to be considered to develop the algorithms. And another important thing is, especially in the case of of vehicles operating in mining sites and all, and in remote construction site or in mining site, the GPS we will get mostly the poor GPS signal. The GPS satellite signals are corrupted by the data noise, multipath errors, clock errors, or atmospheric delays. That is one issue bringing complexity in localization process. Then another thing is the errors in the odometer sensors due to wheel flip and all. So all these frequently changing dynamic environment demands the frequent map update. That is the issue.
Then coming to the extended reach of the off-road machinery. The off-road machinery like excavators and cranes will have the extended reach. As illustrated, you can see that it will have extended reach in azimuth and elevation aspects. And that will add to the complexity of the sensors, because multiple sensors would be required to address the field of view coverage. And that will add to the complexity of the processing as well as the sensor cost and deployment.
Yes, as Rajesh mentioned, multiple sensors, most of the time it is required. And another important thing is the sensors in the moving parts. You can see in the diagram, it is an excavator, and we all know the mode of operation of excavator. Multiple moving parts this vehicle is having. You can see this bucket arm and boom of this excavator is in a continuous motion, and these sensors in some cases we are forced to the demand is like the sensors has to be deployed in attached with the multiple these moving parts in order to get the complete coverage of the hidden areas. Some cases lidar or camera can be attached with the boom or the arm that is required to handle cover the area handled by the bucket region. And these additional perception sensors need to mount on these moving parts to cover the blind spots, and reduces this obstruction in some cases. It helps to reduce the obstructions happened by its own body parts.
Yeah, there could be some usage of companion vehicles to address the extended perception. A drone is one example. The drone can be a companion for this off-road segment, and that will be carrying the additional sensors to improve the perception. And the challenge will be to stitch the data collected by the drone to the static sensors in the vehicle.
Yes, as we said, we can utilize multiple sensors, and these multiple sensors can be attached in different body parts. Body parts will be moving, and in some cases, as Rajesh mentioned, we may utilize the support of companion vehicles with the sensors attached, like the drones with the camera. So what happen is all these things leads to the hybrid sensor fusion algorithms. You can see here in this diagram, the camera is connected and the lidar data is connected with the vehicle body and with the arm. So this camera image and the point cloud which we are getting from the lidar data has to be fused, and which will give the camera lidar composite view. These things provide the terrain view of the surroundings, and these relatively, we can say the static images of point cloud data that has to be stitched with the data from the moving boom, that means a camera. So what will happen is this will give us the faster and simple, not simple, I mean faster and efficient algorithms. The complete, view of the terrain map we can generate and generate using these approaches.
Then coming to the varying field of view, especially when the sensors are mounted on the moving parts of the vehicle, and it has to work in tandem with the static sensors in the vehicle. Then when the sensors are moving, you'll be seeing a varying field of view and varying resolution. And the algorithm need to be so complex to handle the varying resolution and varying field of view to have an surround view of the for the complete vehicle.
Yes, in this slide, this figure illustrates the varying field of view of the sensor. You can see the sensor attached with this arm portion, and each frame we are getting different field of view. So that the one important advantage is because of this, the coverage of the sensor, the complete terrain coverage we will get, but the field of view is changing from each frame to frame. At lower positions of the arm, this coverage on the terrain will be very less, but the resolution will be very high. And these behaviors of terrain data add the complexity of the sensor fusion, and combining this data with other sensors that is also required in some cases. So the challenges are fixing this resolution and the partial updating of terrain map, because we could see some overlapping data in each frame, right? So that will be the techniques and algorithms which we are following.
Then there will be needs for extrapolation or interpolation of data, especially when you have the sensors with a different field of view. The algorithm would require some extrapolation or interpolation, and that is very challenging, especially when you want to have the real-time extrapolation and interpolation of point cloud data. It will be challenging.
Yes, as we discussed all the things like, the extended reach, range, and mode of operation of the vehicle, multiple sensors, and sometimes the sensors will be covered, covered by the body parts. So all these things you can see in this diagram as well, the broader FO view of the sensor, right? So all these maneuvering of excavators require a huge amount of terrain data that has to be handled, processed, and that is it is a it is a brings the complexities once we are working for a resource limited platforms. And these things, these varying field of view and huge terrain data has to be processed, that obviously demands high storage and high processing platforms for handling.
Then there will be challenges associated with the blind spots, especially when you have the large implements like buckets for excavators and wheel loaders. And there will be a lot of blind spots that can create accidents in the field. And multiple sensors would be required and different angles and at different structures would be required to handle these blind spots. And again, the data processing and fusion will be a challenge.
Yeah. What will, we have discussed about the challenges associated with the use cases, and then coming to the approaches what Tata Elxsi is having to solve or develop solutions for these features. One is, of course, we are we can use multiple sensors, multiple low cost sensors we can use, and sensor fusion algorithms can be developed to solve these issues. Another thing is the features can be semi-automation or partial automation or automation on demand kind of features we can develop to handle these use cases. And then, of course, other parties, the remote assistance and remote controlled features with the help of infrastructure assistance, this vehicle to vehicle and vehicle to infrastructure. With the support of those connectivity based features, and we can even provide modular solutions for diverse applications, modular and customized solutions for diverse on-demand applications. These are all our approaches.
Yeah, let us consider the development challenges. The development challenges are mainly associated with the data set availability, especially when you consider AEML solutions. The AEML solutions demands for a lot of data set for training the model, and getting the right scenario from the field will be a challenge, because there's many cases the creating the scenario may be destructive and it may not be practical to happen in the field, and the data set creation is a challenge. And the field validation, the same way that validating the real field, it is another challenge. Creating the real scenarios in the field is going to be a challenge, and there should be some other workaround for the field validation. And preparing the ready to use modules, that is another challenge, because of the diversities in the use cases, we cannot have the ready to use solutions. And the approach would be to use matured building blocks which can be integrated to achieve the required use cases. Then another part is the cost optimization. The cost optimization is challenging, especially in the off-road segment, because of the demand of specialized sensors like lidar and uh, stereo camera to handle the degraded vision situations. These are the main challenges associated with the development.
Yeah, let's address the challenges. How, Tata Elxsi is addressing these challenges that we can discuss in this session. For that, we have multiple approaches. One is, of course, the collecting the data from the real field. That was the one challenge, especially for the AI/ML algorithm development. We do have a synthetic data generation approach and multiple tools and techniques we have for synthetic data generation. That is the one aspect. Second is understanding the physics, understanding the dynamics of the vehicle and everything. We do have the modeling and simulation capability. Then handling the complex terrain and mode of operation complexities, we have hybrid, artificial intelligence and machine learning and computer vision based techniques. Then, for in the case of testing and validation for conducting endurance trials and all, we have offshore alternate vehicle setups. If the real vehicle is not available, we have the vehicle test setups and all in our labs. And we do have developed modular or customized solutions for even for the resource limited platforms and resource limited use cases.
This slide captures our solution accelerators for the off-road segment. And here you can see the multiple solution accelerators and building blocks. And this will cover the most of the requirements in the off-road segment, like motion tracking and localization, SLAM, the perception side, and even handling this degraded vision scenarios, then teleoperations, automation operations, object handling, especially with point cloud data from stereo camera and lidar, and different automation solutions. We have many matured building blocks which can be integrated to achieve the different use case requirements.
Yeah, coming to the solutions which we have in the environmental perception side, we do have the camera-based solutions. For the environmental perception side, the cases like object detection, classification, drivable path identification, for all those use cases, we have camera-based solutions. You can see some segmentation, outputs in this slide. And yes, over to you, Rajesh. Yeah.
Then perception using the lidar-centric solutions. And we have essentially using lidar sensors for various applications, including object detection and classification, object tracking, and point cloud mapping. And even we have solutions for volume estimation based on the lidar data.
Yeah, in the case of perception, not only the camera-based solutions and lidar-centric solutions, we do have the hybrid fusion approaches. I mean, the lidar camera and multiple, I mean, apart from lidar camera, multiple sensor fusion techniques we are implementing for handling multiple cases. And not only, I mean, we can view it as in multiple level. One is from the data level fusion, and the sensor refinement, the temporal and spatial features can be extracted from the data level itself. Then coming to the information level, I mean, the derived features can, the features can be derived from the data level and can be, we can call it as information level fusion. Then finally, in the decision level fusion as well, we are using this hybrid algorithms that eventually help in, I mean, correctly planning the path and navigating the vehicle systems.
Then this is a typical approach when we handle the AML based solutions. You can see that the data sets are created from the real field or emulated thing. It could be from CAD models or physical models. Then even it can be like manipulated field data set. And from all the sources, we'll be able to create a rich training data set for training the model, and which is used for creating the models and the hybrid algorithms. When we say hybrid algorithms, we'll be using CV based, computer vision based, and AML algorithms together to improve the performance.
Yeah. Then coming to the localization, which is one of the critical, I mean, step in the autonomous vehicle navigation, especially even for the autonomous operations as well. So we can see here it is a lidar-centric, I mean, localization. You can see the simultaneous localization and mapping used from the lidar point cloud data, and its visualization you can see in this slide.
And this is the HD mapping approach. Here we are highlighting how the data features are extracted from this huge data set. Especially when you are using generating the HD map, we'll be using the lidar sensors, which will be giving a rich point cloud data. From that, the key features will be extracted, and the data set will be reduced to optimized for creating the map.
Yeah, as Rajesh mentioned, you can see how the key feature points are reduced and how we can create or develop an optimized algorithm. You can see the, I mean, initially a rich point cloud we are getting from the lidar data, and all these points may not require to perform localization or I mean localization. So what we are doing is we need to we have I mean feature point descriptors and feature point identifying algorithms, intelligent algorithms. Those will identify the key feature points, and those key feature points will be utilized for localization process. That's how we can reduce the I mean point cloud data, and which eventually helps in creating optimized solutions for resource constrained, I mean, in order to deploy for resource constrained platforms.
This illustrates the map generation approach. Normally, the data acquisition system will be working at a very high speed, especially the perception algorithm may be at typically at 10 hertz, vehicle control may be also 10 hertz. Localization can also run at 10 hertz. But the map generation will be running at slower speed by the optimization method. This is how we are able to run this real-time map generation algorithm in low-end platforms.
Yeah, this is a typical main ecosystem architecture of our remote assistant application. Of course, it is having the component, the vehicle system. Vehicle system is nothing but it is associated with all the sensors which we are deploying in the vehicle. So that will be the one component. Then the infrastructure, it can be connected to the infrastructure systems and PDAs. And so these are the ecosystem components. And both the remote applications now using the connectivity and the cloud management, security, privacy options, we can do the vehicle prognostics, predictions, vehicle health monitoring, and we can do even fleet control, I mean, fleet management applications, remote controlled operations. All these solutions can be, I mean, deployed with this within this ecosystem.
Then coming to the development setup, what we have physical models generated. You can see that on the left side, we have created a physical model of excavator bucket which is used for creating algorithms for detecting the faulty tooth. The ground engagement tool monitoring solutions. And the middle one is a car platform, modified car platform, enabling the control by wire features with integrated with all sensors like lidar, camera, and other supporting sensors like IMU, GPS, etc. And this is a generic platform where we are using different our autonomy stack, Tata Elxsi developed autonomous algorithm stack, and over which we'll be able to test multiple algorithms for the ADAS applications as well as autonomous applications. And this can be used across automotive segment as well as off-road segment. And the third one on the right is a software-defined platform, which is having the different maneuvering approaches, which could be used for the shop floor applications as well as testing the precision farming applications.
Yeah, now we are coming on to the few of our work samples. You can see in the top left the 3D sensor-based terrain mapping and visualization feature, which we have developed for one of our off-highway. Developed for off-highway equipment for one of our potential customer. The data from the real field is collected, and the corresponding terrain map is generated in order to do the autonomous operations. And the below one is the high definition map generated for one of the autonomous farm vehicle. It's a lidar based map generation. In this terrain, this high definition map, and the rest of the vehicle operations and the navigation control strategies can be defined after this high definition map generation.
The top middle one shows a perception system developed for an excavator, and it is part of the autonomous mining and construction operation. And as part of that, we have developed the 360-degree surround view system with camera and lidar solutions. It involves a high complex perception and sensory fusion algorithms. And bottom middle one is a tractor. It's an after retrofit solution for the tractor to make it working for the autonomous mode between point A to point B. It is equipped with different sensors for the perception, and we have added the actuators and other mechanisms for enabling the drive-by-wire feature.
Yeah, the top right one is another sample. Another important project which we did for one of the autonomous mining vehicle, and it is a mining vehicle control station, entire UI software development. And the below one is an obstacle detection and classification feature for another off-highway equipment. It's a sensor fusion based object detection. The camera and lidar data is fused, and the obstacle detection and classification is performed on that composite high-definition map.
On the top left is a robotaxi or passenger car platform converted into the drive-by-wire enabled features integrated with all sensors, which is the platform for our various autonomous trials and sensor validation trials. And below one is a solution developed for a solar field monitoring system. It's an autonomous vehicle running within the solar field for maintenance of this solar panels.
In the middle top is the transparent bucket feature, especially for this excavator, the construction equipment. We understand that the sensors, connected with the body of the vehicle can be covered by the mode of operation of the bucket. So that particular that particular region of interest data will be lost. So in that case, what will happen is, since we have multiple sensors, so those data will be utilized, and those regions will be restitched, and that those data will be predicted for creating the high definition map. And this use case, we call it as a transparent bucket. In some cases, we do have transparent boom and transparent arm use cases as well. And the middle below one is our simulation capability. It's an off-highway vehicle simulation tool where we can able to simulate the vehicle, the dynamics of the vehicle, and the sensors, different sensor, camera, lidar, sensor models we can simulate. We can even simulate the terrain, the objects, and all these simulation setup helps to generate the data. I mean, for testing and validation, it helps in testing and validation.
On the top right, it is GT monitoring solution. It is the monitoring of damaged tooth of the excavator buckets. It's an AML hybrid solution which uses synthetic data sets for this implementation. And below one is a truck dump area estimation algorithm, which will be detecting the truck, and it will be finding the orientation of the truck for dumping, and it will find out the volume, and it can decide how to distribute the load in that dump area.
In summary, we see, we discussed all the challenges associated with the use cases, and then we seen some challenges associated with the development of such solutions, and we also discussed the approaches what we have to handle all these things. So we can say Tata Elxsi is having technically well-sound solutions, especially for perception, localization, autonomous navigation of these off-highway vehicles. Our main key focus is on efficient perception solutions that can utilize inferences from multiple sensors and like sensor fusion algorithms. Then the optimized solutions that can even deploy in resource limited platforms, which eventually help to reduce the cost of the vehicle. Then platform-centric solutions, then artificial intelligence-enabled solution for custom object detection, classification, semantic segmentation, decision-making, and all. Then intelligent localization and mapping solution with very high precision. We even have the camera, visual odometry, then visual SLAM, and then the lidar-centric simultaneous localization and mapping. Then technically well sound and tested solutions, and all these can easy to integrate and deploy in production.
Yeah, let us get into the videos.
With sensors like lidars, stereo camera, IMU and power distribution system supported by fixtures, mounting rails and racks for capturing the field data. The data captured by the sensors are then used for real scenario verification of Tata Elxsi's terrain mapping and visualization algorithm. Sensor mounting positions and configurations are simulated using the tool developed by Tata Elxsi. The retrofitted excavator remotely gathers high-accuracy terrain and machine data from the job site to give unprecedented real-time insight and visualization of worksite progress. Terrain visualization feature uses a combination of moving and static sensors, and point cloud-based terrain mapping and visualization technology to assist the operator in decision-making.
Yeah, so what we have seen in these demonstrations are like the solutions what we have in localization, mapping, finally the sensor fusion, the camera, lidar, I mean data fusion, which we seen in the end of one of the demonstrations. And in the earlier sessions, we do see the transparent bucket feature implementation, the tester setup what we have, the laboratory testing trials, what we have, everything you have seen in these demonstration videos, right?
Yeah.
Yeah,
So
yeah. Anything to add,
so
Rajesh?
Yeah, I think we are open for the questions and
Questions.
answer session.
so now we can dive into our Q&A session, and our experts would like to share their thoughts on that. Let me start with the questions from audience. Okay. The first question is that what are the localization solution methods available with Tata Alexi, and is the accuracy achieved?
See, I will answer that. The localization solutions, as we described, we have LiDAR-based localization, and it will be augmented by other sensors like IMU, GPS, DGPS, and even we have the camera-based odometry. And based on the requirements, the precision requirements, we'll be going with multiple approaches. And even some cases, we have used multiple IMUs across the vehicles, and that is used for getting the real orientation and motion of vehicle.
All right. I believe that answers the question. Now, going on to the second one, uh, which is the recommended localization solutions for autonomous tractor?
Yeah, tractors, definitely we can go with DGPS. That is some precise, because it's normally such fields will have GPS connectivity, and the DGPS will have a longer coverage. That's one solution. And to have the real motion tracking of the tractor, even we can propose multi GPS and multi IMU solutions to have the exact profiling of motion.
All right. So the next question is, yeah, this is pretty interesting. You have mentioned in your presentation that you can reduce the total cost in developing an autonomous solution for tractors. Can you explain how?
Yeah, interesting, Christine. On options, as we mentioned, we have modular and customized use cases. I mean, customized solutions for diverse applications. So that is the one option, and we have the ready to use building blocks. I mean, already we have ready to use building blocks for all operations like localization. I mean, map generation, navigation. I mean, control systems. Everything we have ready to deploy building blocks. That is the one option. And for the testing and validation, as we have seriously mentioned in the discussion, like the simulation setups, the offshore vehicle test setups. So all these things help us to reduce the overall development cost.
Yeah, thank you, Anjana. I think there is a follow-up question to that also. Whether Tata Alexi has any simulator, especially for off-highway vehicles, for the development activities.
Yes, and then I mentioned we'll be using the simulators, and that is extensively used for creating the scenarios or modeling the vehicle, and even for creating a synthetic data sets for training and validation. And even so many cases we'll be using the physical models also for that.
All right.
The one which we see, I mean, the excavator bucket physical model. That is the one option which we've been especially using for the data set generation for object detection, that teeth monitoring and all. And of course, we have, I mean, we do experienced in the multiple simulators like Unreal Engine, the ZPO, where we can develop the vehicle dynamics as well as terrain and camera sensor models, everything we can simulate and we can do the testing. And of course, it can be used for data generation as well.
Yeah, it is worth saying that even the sensors are really modeled in that application, because the real challenge when we developed the solution, especially the perception solution for the excavator, was like the streaming of the lidar data. And when we use multiple lidars and when they are streaming the data, the streaming itself was taking nearly 100 millisecond for a stream on complete frame. And that was really challenging to collect the data and give a 100 millisecond processing time for the sensor fusion algorithm. Because to model that algorithm, to validate that algorithm, we have extensively used simulated sensors and environment.
So I think we have two more questions. I think after that, it's already time for us to wind up the session. So I'll just go with these two questions that are the first one is how did you overcome the occlusion while mapping the terrain?
Yeah, one point which we discussed is that transparent bucket and transparent arm boom kind of features. I mean, the terrain can be blocked by, I mean, the view of the sensor can be blocked by the vehicle part itself. That we have the transparent bucket feature which we have developed, and it will be included in the demonstration video as well. That is
All
the
right.
one approach we have.
Yeah, it
And
depends
And
mainly, yeah, on the use cases also, because in some cases even we can manage with single sensors. We have solutions with a single camera, even with multiple camera, multiple sensors to handle different use cases. Especially the when the operation is very slow, and some such cases we can manage with single camera approaches also.
the final question is what type of camera are used?
Yeah, the type of camera, and we have experience in using most of the cameras. And if you consider the use cases, and many times we'll be using the stereo camera to generate the point cloud information, and many times it will be required to have the depth information. In such cases we are going for the stereo camera. And even we have IR camera used in some cases, especially when you have the day and night operations. We may have to use the IR camera as well.
all those things will be based upon the requirement what we are getting. We can even customize the algorithms based upon the sensors what we are supposed to work.
All right. So I think the attendees have are clear with their questions and the responses from our experts. So, thank you, Rajesh and Anjana, for this wonderful session. So,
Thank you.
now
Thank you.
let us conclude this webinar. So, to all the attendees, your presence and participation has greatly contributed to the success of this event. So, thank you for your valuable time and we believe that this session was insightful and engaging. So we extend our sincere gratitude to all the attendees who have joined us for this wonderful session. So now we are concluding this session. So for all these people starting their day out there in the world, good morning. And for all others, till next time, it's good afternoon, good evening, and good night from our end. Have a nice day. Bye.
Thank you. Thank you all.